energy, its context, their eigenfunctions, how to solve eigenvalues. They are very useful, and also to understand those s electrons, they do not rotate about the nucleus. It's one of the most common mistakes students make. So that's exam 1. Now we're we look at hydrogen. Last Friday we looked at those orbitals. Today I'm going to show you this is what's the Schrodinger equation for hydrogen, and I think I'll skip the steps of solving the Schrodinger equation. It's a lot. It's too much. It may take I don't know 3 or 4 or 5 lectures to actually go through the steps. So I'm going to skip a lot of steps. But still, you need to know how to write out the Schrodinger equation for hydrogen atom. Later for helium, later for a molecule, because the principle is easy. The principle is easy. Whenever I ask you to write out a Schrodinger equation for a system, this is always your first line, X side equals E side. Again, I mean, right here, we're just talking about the time-independent Schrodinger equation. We don't have time in the equation. We only have x, y, z in the equation. That makes the equation a lot simpler. No time. There's no time. Actually, that actually means the energy of the system is a constant over time. Is a constant over time. So this the energy of the system is a constant over time. And then the second thing you want to realize is Hamiltonian is simply energy plus kinetic energy. So simple expansion. Okay, and then let's look at hydrogen. Let's say hydrogen. Hydrogen is example. If you are hydrogen, you have a nucleus, you have electrons. It's hydrogen. I know in general chemistry, that's how you write hydrogen, H. This is how we write hydrogen after you take quantum chemistry. This is a hydrogen. You have the electron, you have the nucleus, and the electron has a coordinate part, which is a vector, Again, R, I think I'll put this here for your reference. This is R, this is theta. It's very hard for me to draw phi. Phi is the angle rotating about zeta. Phi can be phi. Theta. So over here, theta is 0. I think theta can be exactly pi right here. So that's the range. And how about R? R, we all know that R must be non-negative. R must be non-negative. So the range of that. That's why I did this. But first, it's a lot easier to write out this kinetic energy term in Cartesian coordinates. So it's quite complicated, because you have a proton, you have an electron, or two particles. In each particle, there's 3 kinetic energy terms, x, y, and z. So we're supposed to write 6. But I think I will just neglect the kinetic energy of the proton and only write those of the electron. of electron. And pay attention here, this is the mass of the electron. And actually in quantum chemistry, atomic unit, it's by definition, we define one atomic unit equals the mass of electron. And another way to put it is 1 A dot U dot, one atomic unit of mass, one atomic unit of mass. Question about this. I introduced more atomic units to you. It's not in the book, so you probably need to pay attention to this. We'll define several physical quantities like the mass of the electron to be just one. We can do that. Right? We can even define the mass of this table to be one if it's convenient for us. It's just not. It's not convenient. It's very convenient to define the mass of the electron to be one. You can see if that's one, then this guy will disappear. That's one. Okay. Now my question to you is, how come I can neglect the kinetic energy of proton? Why? So isn't that true that the kinetic energy equals half mv squared, right? Half mv squared, and m proton. I just use mp here, proton, m proton. Okay, it's roughly 1800 times. Is that right? 1800? Do you guys remember the number? Okay, I think it's 1800. Let's say 1800. Okay, so the mass of proton is much greater than the mass of electron. So how come the kinetic energy of the proton is neglected? Oh, very good. And the v is squared. And this v is squared. See, the velocity of the speed of the proton is roughly 1 over 1800. Oh. Times the speed of the electron. Okay, now you know why. Because KE of proton is roughly KE of electron. Okay, so that's for that reason. And in general, the kinetic energy, any nuclei is much smaller than the kinetic energy of electron. Again, nuclei are heavier, but they move much, much slower. And if you look at the expression of kinetic energy, the speed will be squared. Will be squared. All right? So any question about this? And the follow-up question is this coincidence? You see this 1800 here, you see another 1800 here, but it's a reciprocal. Is that just a coincidence, or is we are actually looking at a very important rule in physics, the conservation of momentum, the conservation of momentum. In physics, we say the momentum must be conserved. So now let me give you an example. I need an electron. Okay, this is the electron, pretty small. And I need a proton, much heavier. This is the proton. This is the electron, lighter. To conserve the momentum, again, keep this in mind. This guy is 1800 times heavier than this. And to conserve the momentum, for this guy to move at 1 meter per second this way, this guy will have to, or the electron will have to move at the speed of 1800. 1/800. So that momentum is conserved. Does that make sense? Mm-hmm. And in rotation, it's going to be like this. If the electron is doing rotation. Actually, the proton also moves, but moves at very much slower speed. Does that make sense? So for this reason. All right. And actually, if you read ahead, whatever Schrodinger equation you have read regarding molecules or atoms, always we neglect the motion of the nuclei. And that's an approximation, of course. That means you will get just an approximation of kinetic energy. But later you'll see there's one way to recover that small correction easily. We'll see that later. We'll look at those later. So for now, let's just say the kinetic energy of the protons are negligible, and kinetic energy of nuclei also negligible. So nice. We have only 3 terms. So we have only one electron. Electron is x, y, z coordinates. And then potential energy. So how would you write the potential energy for this guy? Would the potential energy be positive or negative? What do you think? Positive or negative? You have a hydrogen, plus proton, you have negative electron. You guys remember the expression of kinetic energy? Potential energy between charges. We're looking at 2 charges, positive, negative. So just use this equation. Attraction or repulsion between any 2 charges can be expressed as this. Potential energy between 2 charges. Not necessarily attraction, it could be repulsion too. V equals Q1 times Q2 divided by 4 pi epsilon r. Divided by 4 pi epsilon r. R is the distance, Q1 and Q2 are charges. So in this particular case, you have proton, which is positive E. You have electron, which is negative E. So you have negative E squared over 4 pi epsilon. Any question about this? Anybody tell me what this epsilon is? Dielectric constant. Have you learned this? In vacuum. This now means in vacuum. We're looking at this H atom just by itself. So you can imagine we have only 2 particles, proton and electron. Nothing else, no solvent, no other medium. Okay? Don't worry about this. I just want to say, don't worry about this. Because later you will see, in quantum mechanics or quantum chemistry, you also define this guy to be 1 atomic unit. And later you'll see we define this to be 1 atomic unit. M sub E will be defined as 1 atomic unit. Okay, we just try to make it as simple as possible. As simple as possible. Actually, if you look at this, this guy will become negative 1 squared over 2. It's negative 1 over 2. Okay? So, I'll show you a little bit more than this later. So for now, I just want to convince you this 4 pi epsilon is just a constant. It's just a constant. We don't worry about it. We just need to know potential energy. It's proportional to these 2 charges. It's inversely proportional to the distance between the 2 charges. Of course, if you're looking at 2 charges with the same sign, it's going to be repulsion. It's going to be positive. In this case, 1 positive, 1 negative. So looking at attraction, and this is going to be negative. So that's why it's negative. All right, that's it. That's the potential energy operator. And then I'm going to put the whole thing into this square bracket. That's H. Here it is. We're looking at H for hydrogen. Maybe in the exam I'll ask you to write out the Schrodinger equation for a helium atom. Okay? And you have to think about it. If you have a helium, you know how many kinetic energy terms you should write, how many potential energy terms. Okay, it's definitely more complicated than this. In a helium atom, you have 2 electrons. You have 2 electrons, so you have to write this for each of the 2 electrons. And then you have to think about the potential energy. how many terms? How many terms? Well, there's potential energy. In helium 3, exactly. Three particles. The two electrons repel each other. Right, so that's one term, repulsion. And each of the two electrons is attracted by the nucleus. Okay, so, and I know this nucleus has two protons. We assume these two protons are together. Okay, so three particles, one nuclei, one nucleus, consisting of two protons and two neutrons, roughly the same position, and then two other particles, two electrons, so we have three potential energy terms. Do you guys know what's the radius of a nucleus, roughly? What's the radius of a typical atom? The radius of a typical atom is 10 to the power negative 10. Okay, 10 to the power negative 10 meter. 1 angstrom. How about the diameter of a nucleus? Anyone?
So about
1 angstrom? Well, no, the atomic radius is about 1. So that's nucleus plus electron, that's about 1. So the diameter of nucleus has to be lower than 1, and it's
like a millionth that. It's really, really small.
Oh, yes, you're right, it's really small. It's actually about 10 to the power negative 15 meters, so a tiny bit. A tiny bit. The volume is small, but the density is large. The density is quite large. Volume is small. All right. So that's why we can approximately say these two protons are just together. We treat the two protons as a plus 2 charge for helium atom. So again, this whole thing in the bracket, that's H. And you just need to solve this. That's it. That's the Schrodinger equation for hydrogen. And yes, we can solve this exactly. No problem. No problem. If you're patient, spend a few afternoons to solve this. No problem. And actually, I'm going to show you what the other solutions. You have seen the solutions, and you have seen those eigenvalues. Okay? But to solve it, it's quite difficult. Why? Why it's difficult? That's very important. Why it's difficult? See, it's just a differential equation. We have x, y, z. The difficult part is here, this r. You're looking at this operator. 1 over the square root of x squared plus y. This is r. See, if you plug in this expression into this potential energy term, r equals square root of x squared plus y squared plus z squared, and now ask you to solve this. No way. No way to solve this. It's impossible. See, again, this r, the square root, it's on the bottom. It's a reciprocal of square root of, it's, we would say this x and y and z are highly correlated in this expression. So, yeah, it's very hard to imagine a wave function. A wave function that satisfies this Schrodinger equation. So that's why we have to do the conversion from Cartesian coordinates to polar coordinates. We have to do that so that it's going to be r. It's going to be r, not square root of whatever. But unfortunately, we have to convert this in terms of r, theta, and phi. We have to convert x, y, and z to r, theta, and phi. And then we'll have to convert this. Some electrons. So again, this is kinetic energy terms, x, y, and z. And then we just apply this x equals r sine theta cosine phi, y and z, convert it. So I guess you're comfortable with this, right? Derived from the r equals this, x squared plus y squared plus z squared, you just do the math. Tangent phi equals y over x, because if you do y over x, r sine theta, they cancel, it's just sine phi over cosine theta over tangent phi, right? And also similarly, you have tan theta equals square root of r x squared plus y squared over z, right? So, have you seen this? Okay, have you seen these three equations before? Not in this class, in some other class. Physics? No. Calculus? No. Should I show you this? How to get this? No. Well, at least I want to show you one thing. All right, you have you have a z, you have a z here, okay? And imagine this is a proton, and imagine this is an electron. The distance is r, and you have a theta, and then you get this z, right? Again, this z equals r times cosine theta, right? Cosine theta. Cosine. Okay, at least I showed you this. All right? And then you have to do a projection. Okay, that's the difficult part. You have to do a projection of this on the xy surface. And the projection will be r sine theta. So now I'm going to just show you the projection. I'm converting the three-dimensional problem to a two-dimensional problem. So first is a three-dimensional problem. The vector is like this. It's not long enough. Well, this vector is like this, and the distance, the length of this vector is r. And then that z, so this is z. And you have theta. Z is r times cosine theta. And then you project this to xy plane, And this distance is r sine theta. Questions? Does that make sense or not? Okay. If it does make sense, and then we define this to be phi. This angle to be phi. Phi is the angle which defines the x and y. So you can see this distance is r sine theta, so r sine theta times cosine phi, that's x, times sine phi, that's y. All right, so that's why you have this. All right, if you look at this, you may think z is special. No, it's not special. We just arbitrarily choose z to be this r cosine theta, and x, y to be something else. All right, this is indeed shorter. You have to arbitrarily choose one of the three coordinates, x or y or z, to be this r cosine theta. We just arbitrarily choose z. From the three equations to these three equations, very simple algebra. Okay, I'll let you do this yourself. Okay, now this is crazy. So what I was trying to do is I was trying to convert the first derivative with respect to z. Okay, that's Cartesian. I want to convert it to polar. Okay, unfortunately this z depends on r, theta, and phi. That's crazy. So now you can see this wave function depends on r, this wave function depends on theta, this wave function depends on phi. Right? And then the chain rule is this wave function depends on z. True. It can be explained. First, this wave function depends on r, and r depends on z. So you can think of this to cancel. So this is how the propagation goes. You guys learned this error propagation, so similar idea. So how this wave function depends on z, it depends on r, r depends on z, it depends on theta, theta depends on z, it depends on phi, phi depends on z. Right? That's the idea. And then I would say similar expressions for delta phi or delta x, delta phi or delta y, and that's just the first derivative. You look at this, they are second derivative, so you have to do second derivative. And then after, a few afternoons, in the end, you'll get this equation, the shorting equation in polar coordinates. Again, the only reason is we like to keep this r as r. We do not like to have this r equals, square root of x squared plus y squared plus z squared. We hate this, and we like this simple r here. We like this simple r here. We keep this as r. So that's the whole idea. See, we just want to keep this r as r, but not square root of a lot of things. And to keep this as r, we have to expand the kinetic energy term. And you can probably see it's still negative h bar squared over 2me. And now you have 1 over r squared. And then inside you have 3 terms. This term depends on r only. See, there's only r term here. Again, if I give you that question, if I give you a wave function cosine theta, and then you apply this operator to cosine theta, what would the result be? 0, 0. So sometimes it's quite easy to evaluate a eigenfunction and its eigenvalue. But you need to pay attention to details. Just delta over delta, apply this to cosine theta, you get 0. These 2 terms, I don't know if you still remember this or not, these 2 terms correspond to the rotational energy. And you've done this many times. You've done the first in your homework, you apply this operator to 3 cosine theta squared minus 1. That's actually pg squared. You apply this to a constant, that's the 1s orbital of hydrogen. You apply this to cosine theta, it's 2 pg orbital of hydrogen. So you've done this many times already. It's rotation. This part, I don't know how to call that part. I don't know how to call that part. This part corresponds to the motion of the electron relative to the nucleus. You only change this r, you don't change theta, you don't change phi, it's just about the r. Okay? That's not a good name for this guy. I wouldn't call this vibration. I don't like to call this vibration because when you do vibration, usually it's like half kx squared, it's either Morse equation. But in this case, the potential energy is 1 over r. It's 1 over r, it's different. In this assignment too, there's a question. You have to apply this particle in the box. Well, I hope you still remember particle in the box problem. If you have a free particle confined in the box, the potential energy in the box is 0. The particle can never escape out of the box, and then you have discrete energy levels. And if you have a larger box, you have smaller energy space. If you have a smaller box, you have larger energy space. Remember that because the energy spacing is proportional to h squared over 8ma squared. So that h squared, that dimension squared, is on the bottom. So if you have a larger box, you have smaller spacing. You have smaller box, you have larger spacing. And then the question is, use that to explain why the energy spacing of the electron is smaller as the energy increases. So first you have 1s orbital, and then 2s orbital, and 3s orbital, 4s, 5s, 6s. So energy spacing gets smaller and smaller and smaller. For the particle in the box problem, the energy spacing gets larger and larger. So why is that? Actually, one of you asked me this question. The simple answer is, look, the potential energy is different. So of course, they will give you different energy spacing, but more elaborate answer would be, when you go 5s, 6s, 7s, this electron is farther away from the nucleus. It's less confined. Okay? Whenever a particle is less confined, the energy spacing gets smaller. When it's more confined, the energy spacing gets larger. Again, if you think about the box, smaller box, more confined, energy is quantized. Large box, less confined, energy spacing is small. Okay? If you have the whole universe for a free particle, energy will be just continuous. The energy spacing will be just 0. Again, h squared over 8ma squared. If you're talking about the whole universe, let's say this a is infinity, and you have h squared over 8ma squared, you're doing 1 over infinity squared. You're doing 1 over infinity squared, that's 0. That's 0. So that means the energy spacing will be 0. If you have so huge a box, its dimension is infinity, and then the energy spacing is 0, it's continuous. Bottom line is if a particle is confined, as long as a particle is confined, the energy is quantized. If a particle is not confined, the energy is continuous. Okay, so that's one of the homework questions. It's solvable. And I'll show you just the principle, not the actual solving. The principle is, if you want to solve this Schrodinger equation, I'm showing you above, you have r, theta, and phi. They look horrible. They look horrible. You have r, you have theta, you have phi, and you have, whatever, 1 over r term here. I just want to show you the first step is always separation of variables. It's always this separation of variables. We are looking at 3 variables, r, theta, and phi. First step, separate variables. Make it easy. So what we do is we separate variables. We separate this wave function. It's a function of r, theta, and phi into the product of 3 functions, r of r, theta of theta, and phi of phi. Okay, uppercase, lowercase. Uppercase, lowercase. Uppercase denotes the function, lowercase denotes the variable. Questions? And then we plug it in. Okay, I know the next few steps are boring. Or skip all those. So I just skipped all those. Now let's see, we'll have a shorter equation to solve. In this equation, you can see there's only rotation in this term. There's rotation in each term. Okay. And we know that cosine theta is the eigenfunction of this. Good. Cosine theta is the eigenfunction of this. And also a constant can be eigenfunction of this. Good. 3 cosine theta squared minus 1 is also eigenfunction of this. We know the solutions. Okay. And another way to simplify this, we define the whole thing. So this whole operator multiplied by negative h bar squared. So this operator multiplied by negative h bar squared. We just define it to be L squared. Define it to be L squared. Y squared. We'll talk about this later. This L happens to have a physical meaning. The angular momentum. The angular momentum. Then R cross product P. I hope you still remember this. We did that last quarter. In classical physics, it's I want to show you classical physics first. In classical physics, it's a vector. It's not a vector. It's a vector. Right? So if you buy a car, you don't just look at the power, right? You don't just look at power. You also look at the torque. Right? Did you? Well, actually, I don't care. Torque, if you apply a torque, I'm going to hold the center of mass, and I'm going to apply a torque to this. Torque is F cross product R, right? Well, if we use that, R cross product force, I'm applying a torque to this. And after I apply a torque to this, it's going to rotate if I hold the center, right? It's going to rotate, right? And then I apply the torque this way. It's going to rotate. Okay, that's what this torque do. And angular momentum, again, is this R times this P. So this guy moving up. So this part moving up, and this is R direction, this P direction. And the torque, I believe there's a right-hand rule. So this is R, and if it's moving up, so it's moving up. So first this is R, and if this guy is moving up, so this way, and that's the direction of the angular momentum. Okay? Cross product. Actually, I want to show you why this right-hand rule is correct. Unless you have learned this in physics. You did or not? Right-hand rule? Nope.
Yeah.
And why is, did you know why is that the third dimension? So first, this is R, this is P, and then this is, so it's actually from the definition of this cross product, if you look at this. Let's say this is X, this is Y, then the direction of the angular momentum has to be Z. Because if this is X, 0, 0, and if the momentum is Y, so this is non-zero, 0, 0. And do you remember how to evaluate a determinant? Still remember that? So this guy multiplied by this 2 by 2 determinant, which is 0. This guy multiplied by this determinant, which is 0. And this guy multiplied by this determinant, which is non-zero. So you'll see the final result is just has non-zero in the k direction, in the third direction. Okay, mathematically we prove it. All right. Okay, anyway, we shouldn't spend too much time on just physics. Angular momentum. And angular momentum squared over 2m r squared is the rotational energy. I hope you remember that. H bar squared over 2I. H bar squared over 2I. And if you apply this to cosine theta, I think you'll get 2. Apply this to constant, you get 0. Apply this to 3 cosine theta squared minus 1, you get 6, something like that. You get different quantum numbers. Bottom line is, the rotation energy is quantized. It's quantized. Only because, you know, you have to propose a function that satisfies this equation, okay, and you get eigenvalue, and the eigenvalue will be h bar squared over 2I, and then times j plus 1. And j can be 0, j can be 1, j can be 2. And when j equals 0, 1, and 2, j times j plus 1 will be 0, 2, 6, and you do the math, and 3 times 4, and 4 times 5, 5 times 6. Okay, those are the rotation energies. So, questions so far about this? I just copied the same equation here on a different page. Again, this L is operator, is angular momentum operator. We just define L squared is negative h bar squared, and then multiply by the whole, this whole angular operator. Angular operator, it only includes theta and phi angles. Now it's simplified. It's angular momentum squared over 2m r squared. Applied to theta and phi, you get E times theta and phi. And the rotation energy is h bar squared over 2I. This guy's I moment of inertia times L times L plus 1. It could also be J times J plus 1. Again, the difference is it's by convention. When we are talking about the rotation of electrons, we usually use L. Sometimes we talk about rotation of a molecule, HCl. Rotation of atoms, we use J, so that's the only difference. Okay. And L has to be an integer. Okay, now numerical examples. A few questions. First, calculate the angular momentum of one s electron in a hydrogen atom. How would you do that? The angular momentum. And I just asked you to give me the magnitude, not direction, for all those questions. First, calculate the angular momentum of one s electron. Oh, what do you think about the first one? If we talk about physics, the angular momentum an electron, is, okay, L, so that's quantum number times h bar. The rotation energy three-dimensional rotational energy is L times L plus 1. All right. First question, what would the answer be? Now, let's look at one as electron. L equals 1 as electron. Yeah. Yeah, L equals 0. Equals, what's the angular momentum of y as electron?
2.
Yeah. Okay, now, make it a little bit more difficult. How about 2p electron? Calculate the angular momentum of the 2p electron in an excited hydrogen. Well, if you promote a hydrogen from 1s to 2p, it has to be excited. Yeah, it has to be excited. Okay, now, 2p electron. Still the same question. What's the angular momentum of 2p electron?
1, each one.
Very good, very good. How about this guy? H bar squared over 2I, and then times 2. Right, 1 times 2. So anyway, you can cancel this. You can cancel this. The reason I don't like to cancel this because I mean it's easier for me. So 1 times 2 is 2. 2 times 3 is 6. 3 times 4 is 12. You know. So it's a little bit easy for me. If I just treat this whole h bar squared over 2I as a quantum, it's going to be 0 quantum, 2 quantum, well, quantum, 6 quantum, or 12 quantum, or 20 quantum, something like that. All right. So what does that tell you? H bar, it only tells you the magnitude. Magnitude. Of this angular momentum. Well, it's not morning, it's angular momentum. Angular momentum. And magnitude is 1 h bar of 2p electron. It's 1 h bar. Okay? So, it's a vector. It's a vector. It's a vector. So it can point to some other directions. It does not have to point to 0x. So it can be like this, or like this, or like this. Okay? In quantum physics, actually, indeed, it can only have just 3 orientations. One pointing up in the z direction. So, can you tell me what's the z component of the angular momentum? Oh, the length is h bar. Okay, we will learn the magnitude of angular momentum of 2p of h1. So the length of this ruler is 1 h bar. And now if it's pointing up, what's the z component of? Yeah, 1. Well, no, this is 0. This is pointing up. So how about this? What's the z component? 0. 0. 0, right. And how about this guy? What's the angular momentum? What's the z component of the angular momentum? -1. Okay, now you're actually telling me that m sub l can be 1, 0, or -1. Okay, that's what you have just told me. M sub l is the z component of the angular momentum. It can be 1, it can be 0, or 0, -1. And m sub l can never be greater than l. Obvious. The z component can never be greater than the total length of the vector. It's impossible. That's why you have this m sub l. Okay? And they have physical meanings. They have physical meanings. In physics, you have learned that if you have a circular electric current, it can produce what? Circular. It's a very important keyword.
Magnetic field.
Yes, magnetic field. Here you create a magnet. You create it. So it's related to magnetic property of an electron. Okay. So what does that mean? What does that mean? That means, well, if you have 2p z, so the electron actually rotates about the nucleus. If m sub l is positive 1, okay, clockwise, it's doing this rotation. And it's actually a magnet, okay, pointing to the z direction. If m sub l equals negative 1, well, it will rotate still about the z-axis, but maybe counterclockwise, this way. You have a magnet pointing down. Okay, again, this is the hydrogen nucleus. This is rotating. You have a circular electric current pointing up. You have another pointing down. And the third one is, well, it's not rotating about the z-axis. It rotates about either x or y. Let me just give you an example. If it's doing this, there's no magnetic moment in the z direction, but now it does have a magnetic moment in the x direction, in y direction. So that's that. Okay, corresponds to this. And I think that's pretty much it for today.